Hey everybody, it's Professor Fiore back once again for more exciting AC circuits. Today we are going to look at simple passive filters. What are filters? Well, filters are basically circuits that either allow or prevent certain frequencies from getting through. And you're already a little familiar with this concept. Here we have a simple lag network. One resistor, one capacitor. Think of this as just a voltage divider. Now what ends up happening is at very low frequencies this cap opens up, and therefore as a voltage divider all of the generator gets to V out. On the other hand, at very high frequencies X sub C is very small. End result, huge divider effect, we get very little V out. The crossover occurs when capacitive reactance is equal to resistance, right? So our basic capacitive reactance equation, 1 over 2 pi Fc, and all we do is recognize that at the critical frequency, the resistance and the capacitive reactance are the same size. So that will end up giving us, because of the phase angle, 0.707 of the generator voltage across the capacitor. And because power is the square of voltage, right, when you square that, 0.707, which is 1 over the square root of 2, when you square that, you get 1/2. In other words, 1/2 of the power. So we call this a half power point, or a critical frequency. And we simply solve this in terms of Fc, and we find out that that's equal to 1 over 2 pi Rc. Okay? Now, if we do a little plot of this, we do a Bode plot, frequency analysis basically. So I'm going to start this at 100 Hertz, work it up to 100 kilohertz. I can do 1,000 points so we can see a lot of nice detail here. I'm really only concerned about the amplitude. So that's the single plot I'm going to draw. I'm not going to look at delays or phase or anything like that. Okay, here's our curve. So you can see 0 out here. This is in decibels. Okay, just a quick reminder here, decibels, 3 decibels is a factor of 2, 10 decibels. And power would be a factor of 10. If we're talking voltage, again, because of the square, 6 decibels would be a doubling of voltage, and 20 decibels would be a factor of 10 in voltage. So in any case, we can see this coming up. It starts to roll off in this region, above like 1 kilohertz here, and then it continues to drop off as that X sub C value keeps getting smaller and smaller and smaller as frequency goes up. Now we can check this. If you plug these numbers in, a 10 k ohm and a 10 nanofarad cap, your Fc will work out to approximately 1.59 kilohertz. So I'm going to put a little cursor on here and we'll just poke around and see what we can come up with. All right, that looks pretty good. 1.59 at -3. The actual value is -3.01. So this is right on the money. Okay. Now, as this goes up in frequency, you can see this turns into a nice straight line. We can estimate this pretty well. If we come over here, all right, so here we are at 10 kilohertz, roughly speaking, -16. If I went all the way out here to 100 kilohertz, which is a factor of 10, right, that's a decade in frequency, we're sitting at about -36. Okay, so we were back here at around 16, 36, that's 20 dB, 20 decibels per decade. So a factor of 10 in voltage, a factor of 10 in frequency. All right, that's basically what we're looking at there. Okay, so be that as it may, we can do some variations on this. What if I flip these two things? So here I'm going to bring the cap up top, resistor over here, right? So I'm just flipping the position of these two, right? That's what we had. That's what we have now. So same value, same critical frequency. Now at low frequencies, the cap opens up. So again, with our voltage divider, all of the signal will be dropped here at low frequencies. At high frequencies, the cap shorts out and we get everything, right? So instead of allowing through the low frequencies and getting rid of the high frequencies, this does the exact opposite. Right? This limits the low frequencies but allows through the higher frequencies. So again, we can do a little plot on this. And there we go. All right, so our low frequencies are limited. And once again, same values, we'll get the same critical frequency. So I'll just, again, throw this out here and try to find our -3 point right around there. So again, 1.59 roughly. I'm just estimating these. Okay, so I'll do a quick compare. All right, so this thing passes low frequencies, gets rid of the highs. This thing passes highs, gets rid of the lows, right? So it's like a duality. One is the sort of mirror image of the other. Okay. Now you can also do this low pass, this low frequency allowance, if you will. In other words, this guy right there, the original one. You can do this with an inductor. Basically what you do is any of the circuits we're going to look at, which are going to be pretty much all RC kinds of circuits, you can do those with inductors. And what you do is wherever the resistors are, you replace those with inductors. Wherever the caps are, you replace those with resistors. So that would lead you to this. All right, so remember we had a resistor here and we had a cap here. So I flipped these. The equation's a little bit different because your inductive reactance is just 2 pi FL. But we do the same thing. You set up R and X of L as being the same value. Solve the equation, and your critical frequency is now R over 2 pi L. So with these values, I'm going to get the same critical frequency that I had last time. Okay. And we'll run this. And there you go. It's the same curve. Right? Big surprise. I know that kind of flashed there for a second. Maybe you didn't notice it. So I'll go back to the original one. There's the original. And there's our new one with the inductor. So I get the same exact thing. Generally speaking, we'd actually prefer to do circuits using caps rather than inductors because caps behave more ideally than inductors do. Inductors have issues with internal resistance, coil resistance. We have issues with stray magnetic fields and things like this. So caps are a little bit better behaved, and if we can, we'd rather use caps than inductors. Now with simple kinds of circuits like this, you can do it without caps. If you want to look at a little bit more complicated kind of a response, we're going to have to perhaps use inductors or go to an active circuit using transistors or op amps to do something a little bit more complicated in terms of the response out here. But, for what we're looking at here, simple cap resistor combination will work fine. Okay, so let's look at a variation. Remind you back where we were with our original resistor and capacitor. So let me throw a resistor in here next to the cap. Now this does something kind of interesting. In the original circuit without the resistance, remember, as high frequencies continue up, this X sub C gets smaller and smaller and smaller, and what we saw out here was the signal at the output getting smaller and smaller and smaller, right? Simple voltage divider. By introducing R2, this creates a lower limit. In other words, this total impedance can never be less than 1K. So therefore, the divider is never worse than a 10-to-1 divider. So what we're going to get is what's called a shelving response. I've extended this out to 1 meg instead of 100 kilohertz. So you can see it a little bit better. But this basically starts again with this little curve, 1.59 or so kilohertz. Comes down, straightens out. But then we start to get into this area where the 1K, this R2 down here, starts to come into play. And that limits things, right? So that flattens things out instead of just continuing on down. Now, if we took a close look at this, we would notice that the critical frequency is in fact a little bit off from that original 1.59, right, where we would expect a -3 dB. In fact, let's see if I can get close to this, right about there. So this is a little bit lower, right? We're looking at about 1.46. Why did it drop? Why is it not 1.59? Well, it's because of the total impedance that the cap sees, right? The Thevenin equivalent that's driving this is now 11K, not 10K. So a simple solution to that, if you wanted to keep the 1.59K that you had originally, you can just drop these resistors a little bit. Turn this into a 9.1K, turn this into a 910 ohm. Those are your nearest standard values. And you'd have about 10K total. You'd end up with that same critical frequency that we had before, and you'd get the same kind of shape. Okay, so you can play with this with the value of R2. If you bring R2 smaller, you brought it down to 500 ohms, 100 ohms, whatever, then this curve would continue out farther along before it flattens out again. Okay? And where it curves, that critical frequency is basically controlled by these two values, this cap and this resistor. All right, so you make this smaller and smaller and smaller. This is going to extend out farther and farther and farther and farther. So what good is a shelving type response? Well, a common usage for a shelving response would be something like a bass or a treble control that you might see on your home stereo. Those are of course, adjustable. This is not adjustable. This is a fixed kind of thing. You could put a resistor pot here instead of just a simple resistor, and you could get a little bit of control, but that would also do a little bit of the frequency shifting I was talking about. And there are active ways of doing that to have the shelve change, where it hinges, and to actually have boost as well as cut. We can look at that with active devices like op amps. But this is a nice little variation, okay? And you can do the same thing with the inverted version of this. In other words, the kind where we would be up here and then come down and do this, okay? So in other words, the high pass version instead of this low pass version. All right, continuing along. What if we wanted something that was a bit steeper? In other words, I'm going to go back to my original one. All right, this is my very first circuit. And I have this rate, which we said was, 20 decibels per decade, basically. What if I want this thing to come out and then dive a lot faster? In other words, I want the attenuation on these higher frequencies to be more extreme. This isn't enough. Okay, what do I do? Where do I go from there? Well, we have a couple options. Probably the simplest thing we can do is to simply cascade sections. So here's a second section I've tacked onto here. Now, the nice thing about this is it uses only capacitors. The problem is we're a little bit limited. There's a little bit of sort of hamstringing, if you will, in terms of what we can do here. One of the issues is that this resistor and cap, right, will partially load C1, and that can produce some shifting in the critical frequency and the shape of this thing. So to kind of isolate them, what we can do is make the second piece, in other words, the thing that's in parallel essentially with C1, we can make this a higher impedance. In this case, I've just punched them up by a factor of 10, right? So R is 10 times bigger, and to get the same critical frequency, I make C2 over here 10 times smaller, okay? So essentially what's going to happen is at V out number 1, we're going to have that initial kind of curve, kind of like this, and then at V out number 2, that'll happen again. So this will be additive, all right? So let's run that up, take a look at it. Okay, let's get a legend out here so you can see what's going on. So V out number 1, that's this guy, is the green. This is the original. Notice the scale over here has changed quite a bit, okay, just to fit this all on here. So this is the original that we were looking at. And then V out number 2 includes the second RC divider, so that makes things attenuate even faster. Now there's 2 of them. Remember, originally we were talking about, a 20 decibel per decade attenuation rate on here. What are we looking at now? So I'm going to park this element over here, park this guy over here. You go over there. Put that down there. Okay, so we're going from 10 to 100K, and you can see we're going from negative 32 to roughly negative 72. So we're looking at about a 40 decibel per decade roll-off. Right? 20 from the first one, 20 from the second one. There you go, 40. All right. Okay, so that seems to work. Now the issue that I sort of alluded to initially is that we're a little limited in what we can do with this kind of thing. Like I said, the nice aspect is we just have caps. But if we actually went and picked up an inductor, we could make a simpler circuit. So here I just have an inductor, cap still here. I've just thrown this in along with my original resistor. Okay, so we can maybe compare this to the original circuit where I just had a resistor and a cap. Okay, now there's that same cap. I've changed the values here, but that same position for the cap, a resistor and an inductor. So what we have now is essentially a second order system. As frequency goes up, X sub C gets smaller, and we've seen what that effect is, but X sub L actually gets bigger. So we sort of get like a double bang for the buck, okay? And this is going to give us something like the maroon curve over here. It's going to be a much faster curve. In fact, if you take a look at this, what you really have is a series resonant loop. Okay, so the R1 here is the total resistance in the system, which would include the R coil. So I'm not going to draw a separate R coil here, but you are limited by that. You can't get any lower than R coil. Now, what ends up happening in a series, little series resonant loop? Well, you get this response that was going to have a little peak around the resonance, depending on what the damping factor is, what the Q is. Right? Damping is the reciprocal of Q, the quality factor. And that's essentially looking at the ratio of your X sub L and your R value. Right? So as I adjust the R value, we can change the peakiness, if you will, of this output shape. All right? So let's do analysis on this. And here we go. All right, so we have that same kind of curve. Let me go back to the original one. All right, again, the scales are a little bit different. All right, so that's 0 to minus 40. And then this one, right, we're going from plus 20 to minus 80. But it's still that same general kind of shape, right? Getting rid of the high frequencies. But if we, again, look at the attenuation up here, once it flattens out, you know, here we are sitting probably somewhere around, without getting out the cursors, we're sitting somewhere around minus 35. And over here we're sitting around maybe minus 75 or so, right, at 100K. So there's our 40 dB per decade roll-off that we had with the Cascade circuit, okay? So, you know, a quick comparison, right? In other words, this guy. However, this sort of pokey kind of roll-off that we got, notice, if you look carefully, there's a little bit of a peak here. This is the resonant peak that we're getting. We can control this peak by the size of R. So if I were to make this a little smaller, let's say we make that half the size, I'll go to 500 ohms. That is going to make a sharper, peakier kind of response, right? This would be an underdamped, a lower damping factor circuit. All right, so you can see that thing punch up. And the smaller I make this resistance, the bigger that resonant peak is going to become. Right? Lower limit on that, again, is whatever our coil happens to be. If we go the other way, if I make this bigger, I'm not going to make it 2K, this is going to have a more sort of relaxed, slower kind of response. We're not going to see the big resonant peak there anymore. All right, so we notice we've shifted up here from 0. So there is no peak. So it's just kind of pokily, pokily, is that a word? It kind of, in a pokey manner, how's that, drops off there instead of that little bit of resonant peak that we saw before. But ultimately, that roll-off is still going to be in that 40 dB per decade range. Okay? So you have a little bit more control over this. It uses fewer components, but it does use an inductor. Oh well, you win some, you lose some, right? You gain, whatever. All right, so there's a nice little overview of the circuits, right? So we started off with this little RC circuit, which gave us a nice, simple, low-pass response. If you swap the positions, we get the inverted response, a high-pass response. We could also make that low-pass response with an inductor. Remember, you just replace your caps with resistors, replace your old resistors with inductors. You have to recalculate the values, but that will give you the same effective response. Okay. Then we can add a little resistance in here to get a shelving response. Okay. We can do a cascade, which will give us a faster roll-off. Although, without a lot of control, we are a little bit limited here, but it doesn't have to use inductors. But if we do go with the inductor, right, it's a simpler circuit, and we have a little control over that resonant peak, okay, that area right here. Okay, so that's a good comparison just between these two. You can see exactly what's going on. And at the extremes, right, up here and down here, it's not changing. It's just that resonant peak that's changing, right? Damping factor of that resistor. All right, beauty. We'll see you next time.